Thanks a lot, Nathan. So I hope you can hear me on Zoom. Thanks a lot. So this is going to be a two-part talk. I'm going to be talking about a lot of the fluid aspect of things that I'm interested in. So I'm interested in turbulent flows, fluid flows, and I'm going to give you a flavor of the things that my lab at UNR is doing, and then Floris is going to take it away with his cool biology inspired stuff. So essentially, there's not a ton of machine learning in this talk. I would still think of myself as a more classical person, but definitely there's a lot of scope for leveraging ideas from machine learning. So the first thing that I want to bring up is fluid flow systems are challenging and hard. There's a lot of scientific challenges. Oh, I can't show you my mask. There's a lot of scientific challenges, especially in flow separation, dynamic stall, reverse flow. When you have multi-physics systems like fluid structure interaction, there is flutter, there is noise. So there's lots of scientific challenges in fluid flows. There's also it's very rich and interesting from a fundamental point of view. So there are triadic interactions, nonlinearity, high dimensionality, and we saw some great talks in sensor actuator placement. Hart talked about yesterday about complexity versus accuracy. So there's a ton of fundamental challenges in fluid flows as well. My approach is going to be this kind of fourfold points that I put out here, which is characterize these interactions on a network or a graph, then build interpretable models of these using ideas from graph theory and data science, identify some time-varying flow structures of significance for flow modification, and design some feedback control strategies. Okay, so this is basically a big part of my PhD work. This was with Sam Tyra at UCLA, and my collaborator was Steve Brunton in these efforts. And if you see the left, these are some data-driven networks that we have extracted from laminar flow. So you have a body and you have a flow over the body. What we wanted to do is represent that on a network. Now you'll say, well, a network is made up of nodes and edges. What are the nodes and edges in continuum? So the idea is, what we did is we said that the modes of the flow are going to be the nodes. It was rhyming, so we were like, what the hell, let's do it. But the modes are going to be the nodes, and then the edges are going to be the energy transfer interactions between those modes. Okay, so Kritika in the earlier talk gave a beautiful instruction on POD. We actually use proper orthogonal decomposition, or POD, to decompose the flow into modes. And then what we do is we basically perturb the flow to extract interactions between those modes. And that's what you see on the left. And once you have the interactive graph, what you can do is you can do some beautiful control, because you exactly know how energy transfers from one mode to the other. And what we wanted to achieve is this unstable equilibrium in these laminar flows, which gives you nice properties with drag. On the right, we show some physics-based networks, which is basically discretizing a turbulence network. And I believe Lena mentioned about taking grid points as nodes. That's exactly what we do here. Grid points as nodes. In fact, the nodes are grid vortices, so they have a particular strength, and they are connected to each other by these edges, which are based on this metric that we call induced velocity. This just purely comes from physics and theory. But once we have that network representation, what we see is we get a beautiful scale-free characterization of turbulent flow. So this is popular network literature where you get these distribution of hubs and low-linked elements connected to each other in a beautiful format. Okay, so where do we go from here? Okay, we can represent fluid flow, or something that is a continuum system, on a graph. Now, where we want to go, at least in my group, is we want to take these ideas to multi-physics systems, in particular fluid structure interaction. So what if you have a structure that is compliant, that is flapping in this flow, and there is a fluid? Can we map the interactions between the fluid and the structure on a network? So that is kind of our initial attempt. This is just ongoing work. I just joined in UNR in 2020, so Sam is my first PhD student. So we've been attempting to build these kind of interactive models of fluid structure interaction using a network framework. So now you ask, okay, you built these models for fluids, but how does that tie to a structure? It's not very intuitive. So what we do is we leverage ideas from potential flow theory. And I mean, this is a theory in fluids. Basically, when you study an introductory course, usually you start with potential flow. But in potential flow theory, basically, there's an idea where you can actually get the something called as a vortex-led strength of a structure if you have the structural displacement and you have an idea of what the wake vortices are. So we take a high dimensional flow, we take that information of the wake vortices and the structural displacement, and then once we have all of the information, our nodes become the vortices and the edges become induced velocity. And what we can do with that is, again, we can describe this kind of complicated fluid structure interaction system on a network, okay? Now you'll say, okay, you represent it on a network, what's the actual use of this? What we want to go from there is basically build a reduced order model. So we want to build something like a reduced representation of these physics. So what we do is, so on the left, you'll see is a random network. On the right, you'll see something more modular. So we want to build these communities of things in this fluid structure interaction system where we can then compress the representation of the complicated system of fluid structure interactions onto reduced representation. So on the right is just showing you our initial attempt of doing so. We have these kind of compliant structure that is flapping. This is, of course, right now in 2D. We want to extend it to 3D. And then what we can do is we can extract this kind of coupling matrix. So this matrix just gives you how these, these individual vortices in this reduced representation are interacting with each other. And when you have that, you can actually build multiple, interactive models of these through, say, a limit cycle, so something where you have this periodic vortex shedding, or on the right, where you have, say, gusts entering the flow. So I basically, hit the system with some perturbation or disturbance, and I can see exactly how this kind of network evolves over time. So, okay, you have a good representation of the interactions in this kind of, I want to say 10 by 10 matrix. So that's a good representation of, of course, if you have a fluid flow, you have a lot of degrees of freedom. It's a large system. But what more can you do with it? But what more you can do with this is you can leverage ideas from network theory to say, hey, what is the in degree and out degree strengths of these individual matrices, which is basically just a row sum and a column sum in this case, right? You can do more with it, but in this case, the out degree is just the summation of the structure to fluid coupling, and the in degree is just the summation of the fluid to structure coupling. And what it tells you is on the right is of the figure. So you have two figures here. On the right end is the rigid body, and on the leftmost end is a compliant body. Same case here. Here I have this addition of an external disturbance or a gust. So again, you have a rigid body and a compliant body. What it starts to do is it starts to identify these spikes when a gust enters the system. So that's pretty cool. As well as if you have just a limit cycle, just a periodic limit cycle happening in the flow, basically you can see that these in degree and out degree distributions kind of, don't have this large oscillation because there is no compliance associated with the structure. So the rigid case is pretty much flat. And then when you go to these more compliant cases, you start to see more and more periodicity or more and more fluctuations in this in and out degree. So the idea, at least the question that I had, possibly we'll get an answer to by exploring machine learning is, can we bake such insights of interactions into machine learning models to improve predictability and interpretability? Okay. The other thing that I'm really interested is, again, in Hotstock, I've been reading a lot of Hot's papers, is, conservation laws. So basically, the other thing that, is very interesting in fluid flows is, can you modify fluid flows by taking advantage of conserved quantities or conservation laws or these integral invariants in the flow, Okay, and why is that useful? What we've shown is this is super recent. This is under review in JFM, but essentially what we've shown is we can accelerate or decelerate the turbulence cascades by just modifying quantities, these integral invariant quantities associated with the flow. So basically there's a bunch of math there, but you can see the forcing, we force the Navier-Stokes equation, but the forcing is just built off these kind of triple cross products. It's like super simple that we can, once we can, determine what B1 and B2 is, which requires knowledge of the invariance of the flow, we can force the energy of the flow or separately from the entropy or modify both together. So basically, there are specific structures that get excited when you only modify energy versus modify entropy or modify both. So, one of my students is working on extending this to 3D, basically 3D turbulence. So the idea is if you can, have an idea of what the integral conservation laws are, you can perform this approach and you can identify not only time-varying flow structures, but also discover some equilibrium solutions in the flow, okay? But again, everything that I'm showing here is that I have the knowledge of the integral invariance or the conservation laws. But the main question that we want to drive towards is we want to discover these conservation laws from using machine learning. Okay, so this is kind of an approach that again I'm super excited about, which is using flow control or data-driven ideas and network science ideas for flow control. Here, what I just show you is basically there's a complicated flow, which is turbulent flows. We take that data, we partition that data, and we build control algorithms to just from data, we basically control where these trajectories of the flow will go. So basically, I want the flow to go towards low drag state by minimizing drag. So again, the idea would be, can we build better optimizers and estimators for flow control? So John Wright talked about better optimization strategies. We want to leverage that for flow control. Again, there are machine learning approaches that I would like to bake physics into. So this is physics injection. So can we infuse these ideas in machine learning? So this is, we have people that are coming into my group to help related to this AI Institute project, and I give the floor to Floris for this presentation.
Awesome.
Sorry, I'm not sure exactly what's happening.
There you go. The presenter, and it's not going out.
Never had it. Oh, I think my computer's just thinking too hard.
So you here? Let's try one.
Yeah, it's still it's thinking. That's the
Oh. Okay, something here. So
I don't know where my mouse is now. Oh, there it is.
all right, now go to here. Just hit. I think you hit that.
This guy?
Yeah. No. Okay.
Oh my God. What?
Yeah, just do that thing.
Yeah.
All right.
There we go.
All right.
Sorry for the oops. Technical issues. Can I move this guy? There we go. Okay.
So I'm going to tell you a little bit about some of the stuff I've been thinking about recently. My work is a little different than I think most of the people that have presented so far. I work at the intersection of control theory, data science, insect behavior, and neuroscience. I'm going to try and tell you a little bit about how they all fit together in my mind. And I think best when I think about very specific, very concrete problems. And so I'm going to tell you about a very specific, very concrete problem today, a little bit, less broad than some of the other talks we've seen. But one of my goals with this AI Institute is to figure out ways of using machine learning and AI to take the very specific concept here and generalize it to bigger problems. And so that's where I love to collaborate with people to make that happen. So what you see in this photograph is a long exposure photograph of a fruit fly following an odor plume upwind towards the strawberry. And you see a couple patterns in that behavior that are very characteristic. So you see this kind of moving back and forth, this zigzagging, we call that casting. Traditionally, that's been thought of as a mechanism to help them find the odor plume. But I'm going to tell you today that I think there's more to it than that. What you can't see in the picture, but as a sort of a cheesy cartoon, I've overlaid a simulation of a turbulent odor plume. And so the challenge that the insect is trying to solve is how does it figure out where the source of that odor plume is when it only has access to individual measurements as it's flying along. There's no gradient for it to follow. It's a very hard problem. And a big part of that problem is for the fly to figure out where is the wind coming from, because that is generally where the odor plume is going to be coming from. And so I've worked most of my PhD and postdoc on figuring out how the fly sort of follows the plume, but now I'm interested in how does the insect figure out where the wind is coming from, because that's really the fundamental problem in this challenge, in my opinion. So this ends up being a nonlinear state estimation problem. And so for those of you who aren't familiar with this kind of terminology, what the insect is trying to do is estimate an unmeasured state given other measurements, presumably with some access to some kinematic or dynamic model. So mathematically, how do you take some, say, 3 measurements and put that through some nonlinear function and get some estimate of some other measurement that you don't have access to? So a traditional engineering approach might be to use, say, an unscented Kalman filter that requires a system model, a system dynamics model rather, and it's computationally expensive. And so I want ways to solve this problem that you could run on a very small, a small robot very quickly. Insects are proof to me that these alternatives do exist, but we have to find them. And so I believe there's kind of, in my mind, two options. One is looking at insects for biological inspiration. So that's what I tell you about today. But I think we can learn from that to generalize this idea using machine learning AI methods. So there's kind of a few steps in this process. The first step is we should know whether or not it's even possible to solve the problem we want to solve. So there's tools for that, nonlinear observability, Gramians, and so forth. We're not going to talk about that today. The next sort of question is which trajectories are most feasible for actually solving the problem, given noise-free measurements and a system model. For that, we do have tools. The empirical observability Gramian is one. There's definitely relationships to what Kritha talked about. We're not really going to talk about that today either, because it's solved. Then the next sort of slightly more complicated question is which trajectories are best, given that you have very noisy measurements and you have no model of the dynamics. So that's what I'm going to mostly talk about today. And then moving beyond that, which I'll also talk a little bit about, what trajectories enable the existence of a closed form nonlinear observer, one where you don't need a system model, you don't have to do iterative methods, you just get the answer because you've sort of simplified the problem to the point where there is a closed form solution. And then can you do all of this just with data without any knowledge of anything else at all? So those are some challenges I think are interesting. So now let's dive into this concrete example. How might an insect or an insect-sized robot figure out the direction of the ambient wind given the information they do have access to? So if you look at it, fly brain, we know a lot about fly brains now. And so right in the middle there's this object called the central complex, in particular, this little donut shape called the ellipsoid body. And in that region of the brain, they're encoding a lot of angular information, directions of different sensory modalities. So let me show you a video. This is not from my lab or anything. This is just a good video showing what is known and possible. And this is already 7 years old, so we know a lot more than this. In the upper left, you're going to see a movie of the neural activity in the ellipsoid body in the fly's brain. And the location of that little red yellow spot is going to show you where on that donut the activity is most active. In the upper right, you're going to see a picture of a blue stripe that was being shown to a fly that was in this little setup. And the fly is in the lower left here, walking on a little ball. And so the fly is looking at the stripe. The researchers are measuring what's happening in that ellipsoid body in the fly's brain. And then on the lower right, you'll see where the blue stripe is relative to the ball. The ball's moving and the stripe is moving. And where the activity is in the fly's brain. And what you'll see is that they follow each other. So the fly is essentially encoding the location of that stripe in polar coordinates in the center of its brain. Okay, so we know now that not only do they encode that head orientation relative to the world or the world relative to their head, they also encode the direction of visual motion that they're moving. And they also encode the direction of the apparent wind that they experience. And so the first question is it possible to extract the ambient wind direction from those three angular measurements? It's not trivial, but the answer is yes, but we're not going to go into it now, but you can read my paper on that if you want to see the math. Now, one question is, why use just those angular measurements? Well, the simple answer is that it's less sensitive to changes in sensor gain because you've essentially eliminated that by taking the ratio of, say, the forward and sideways direction. You've kind of eliminated a component of the sensor gain. And it's also a lot easier to self-calibrate sensors. You can self-calibrate the magnetic compass in your phone by kind of rotating it around. And that's because it's all sort of angular aspects to it. So now the question we're going to focus on is, how do you do this? Or how might a fly do this, and what trajectories are best? So again, we're going to dive into some real detail here. So this is a little triangle that kind of is the center of everything. The fly has some orientation. It's got some ground speed. There's some ambient wind blowing on it, and it experiences some air velocity or apparent wind that's the vector sum of those two. Now, in order to do everything in angles, we have to define some angles. The key ones here are going to be the angle of the air velocity relative to its orientation, the angle of its direction relative to its orientation, and the angle of its orientation relative to some global coordinates. So those are the three measurements we have access to. We can write out a nice geometric relationship from the law of sines. We can simplify that a little bit by knowing that we don't care about what the ground speed or the wind speed is. And so we can just use a ratio of the two as a new kind of variable. But we only have one equation here and two unknowns. So it's impossible to solve that problem. Those are our two unknowns there, the zeta being the ambient wind direction. We can simplify things a little bit just by reducing the number of variables and reorganizing things. That'll help, because the next thing we're going to do is take a derivative with respect to time. Now we have two equations and two unknowns. So as long as we have some time series data, we can solve this problem somehow. It is possible to solve that. There's only one problem. Sorry, we're going to first convert this to in order to solve it, I'm going to convert it to a convex problem. So it's very fast to solve. And then I can use that formulation to determine what trajectories minimize my errors, and then we're going to find some closed form solutions. So these are really the problematic terms. We have a product of two unknowns, and so that's what makes it non-convex. So the first thing we're going to do is we're going to say, well, the wind direction is going to change kind of slowly. So zeta dot is 0, so we can get rid of those terms. And now it's sort of convex. We're going to skip all the details because that's not what I want to tell you about. But there's a few things I do want to tell you about, which is the architecture of this solution. So I'm taking these three angular measurements. I'm going to do some smoothing because we have really noisy data. And then with that, I'm going to take a derivative. So now I have these 6 estimates. And then I'm going to take those estimates over some window of time, tau, and I'm going to take all that information and I'm going to dump it into a convex optimizer, and I'm going to get some estimate of the wind direction. It's only good down to plus or minus pi. So we have to do a little extra work to figure out what that disambiguation constant is. Again, the detail there doesn't matter too much. I just want you to kind of see the overall architecture. So let's see it in action. So here's a sample trajectory of an agent making 90-degree turns. It's got variable ground speed. Here's a sampling of its sensor information that it has accessible, those 3 sensor directions that we have. So running it through that convex optimization routine, we can get an estimate of the wind direction, the little red dots relative to the black dots, which are measurements of real wind that this agent was simulated inside. We can do this for different turning frequencies. So the agent could turn very quickly or very slowly. And on the x-axis, sorry, this thing is in the way here. We could integrate information over different time periods. And you can see there's an optimal kind of area to this. So to add a little bit of insight into what that means there, I'm going to overlay two other curves here. In blue, I'm showing you what is the average change in wind speed as a function of this time tau. So what this blue curve is showing you, if I can find my mouse, oh God. The blue curve is showing you that after 1 second or so, the wind has not changed very much, but after 250 seconds, there's a good chance that it's changed by 90 degrees or more. So you don't want to integrate information over too long a period of time, because then you're not going to get a good estimate. On the other side of this red ellipse here, we have this black line, which shows you above that, you're getting more than 1 turn per unit tau. So you're collecting more information from different directions of movement in that one window of time where we're integrating information from. And so you want to kind of lie in between those sort of spaces. So now we can see what happens if we change the magnitude of the turns. So for very small turns, it's hard to get a good estimate. As those turns get bigger and bigger, it gets easier and easier to get a good estimate. And now the next step, right, here's an example of sort of an edge case where we're only taking information from a very short period of time, but the agent is changing direction very quickly. We can get decent estimates, but there's a lot of noise in there. You can get rid of a lot of that noise by integrating information over a longer period of time. Now, if you add more and more and more sensor noise, we start to see some other patterns. As you increase sensor noise, the agent has to turn more slowly. That makes sense because you want to filter out a lot of that noise. If the agent was turning too quickly and you filter out a lot of that noise, you're also filtering out the information that's provided by those turns. And then one other kind of interesting observation, when you really crank up the noise, you can think about what happens with different types of trajectories. So here, I've been showing you all trajectories where the agent is always pointed in the direction that it's moving. But an alternative would be if it's always pointed in the direction of its airspeed, which is shown on the right. And it turns out for very high noise situations, this does a little bit better. And that caught me by surprise a little bit. And so I wanted to dig into why that was what was happening there. And sorry, my computer is like freaking out. So if you take these two different types of trajectories, on the left, we have the constant size, meaning that the fly is always pointed the direction that it's moving. And on the right, we have what's happening if the fly is always pointed in the direction of its airspeed. And we can look at the mean absolute error in two of the sort of sensor estimates that we have. And for one of those, the orientation, that estimate gets much, much better. You see here, if the fly adopts a constant gamma trajectory. And the reason for that is that its orientation is only changing very slowly, which you can see in this trajectory. And so it's a lot easier to smooth that estimate out and to take a derivative and so forth. And that ultimately enhances the accuracy of our ambient wind estimates. So now we get to kind of the most exciting part, is all of that was based on what I consider to be a pretty computationally expensive convex optimization routine. Now, in the grand scheme of things, maybe that's efficient, but it's not good enough for me and a tiny robot. But if you introduce some control, if you say my agent has to fly with a constant ground speed, the math simplifies, and you can actually write out a closed form solution for the ambient wind direction. It comes out to kind of a nasty algebraic equation, but the fact that we can write out a closed form solution means that you could evaluate this very, very quickly. This is with continuous measurements. If you do it in discrete time, you can get a slightly different formulation. You can reorganize that. And the only reason I do all of this is to show you in the next slide, I'll show you that each of these terms contains derivatives. But before we get to that, what I've shown you so far, I want to match that up to what we see in the biology. So plume tracking flies generally exhibit these very large turns. They're generally moving with constant gamma. They're generally pointed in the direction of their airspeed. And they're also generally trying to maintain constant ground speed. So what we see the insects doing seems to be exactly what you would want to do if you want to have a very accurate and very mathematically simple estimator for the ambient wind direction. So this is still a hypothesis that we need to do some experiments to test, but it seems pretty exciting. And the overall kind of theme here is that we could simplify this multimodal sensory integration through active control, and tying it in with a couple other talks. The active control that we're using is to basically introduce invariant quantities. We're introducing an invariant quantity by saying we're going to control velocity so it remains constant. We're going to control the direction that the airspeed of experienced airspeed so it remains a constant. And those decisions really simplify the estimation problem. So now back to the derivatives. You see there's a lot of derivative terms in these expressions. It's a little easier to see on the top one. Don't worry too much about the bottom one. So numerical derivatives play a fundamental role in this kind of estimation, and also in a lot of the other tools that people have been talking about. So just to summarize a couple of these insights, some trajectories provide better estimates than others, in particular ones where you make a large turn. With high levels of sensory noise, certain trajectories offer additional advantages by facilitating that differentiation step. Some trajectories allow for closed form solutions, which gives you the opportunity to have very fast estimators or observers. And so the challenge for me in the context of this AI Institute, I think, is can we generalize these insights with automated methods to more arbitrary systems rather than this very specific example. And then the last point that I just want to highlight is that a key part of this is getting accurate model-free derivatives of noisy sensor data. And so in the last couple of years, I've been working with Nathan and others to develop this Python package, which you can now download and use. If you have any need for a numerical derivative of noisy data, I hope you try this out. I think there's about 20 methods implemented there, including automated parameter estimation routines, so you don't have to worry about that stuff. Very useful tool, I believe. Please use it. Please contribute if you find that you'd like to add something. And the last thing, if I have just one more minute, is just to highlight one of the other tools in my lab that I didn't talk at all about is we're doing a lot of experiments where we're using optogenetics to remotely activate neurons in the brain of a freely flying fly. So just to show you what that looks like is we can take a red light sensitive ion channel and express it in olfactory neurons in the fruit fly. We can put that fruit fly in the wind tunnel where we can track the flies in 3D in real time and then turn on bright red lights to activate these neurons, olfactory neurons mostly in our case. So here's I think this is a little video just to show, this is not with a fly, but this is just with a little simulated tracking target showing you when the tracking target is in a particular volume, the red lights turn on. In the actual experiment, that triggers a virtual odor experience for the fly. So here's a little animation of what that looks like. So we had a fly flying along. It passes through some volume. The red indicates that lights turned on. And then the fly immediately turns upwind and it starts doing this casting behavior. So we're able to replicate these natural olfactory behaviors using a completely controlled virtual stimulus. Here's a time series showing that after this flash, the flies turn upwind. They're all concentrated. Again, this thing is in the way here. But the flies all turn upwind and then they start casting where you see kind of density over here later in the trajectory. We can also induce object approach, which is another classic olfactory driven behavior. So this is work being done by my postdoc, David Stupsky. And with that, I'd like to thank everyone else in my lab, funding sources and so forth. I'm happy to take any questions if there's time.
Time just for a couple quick questions from Floris and Aditya. Do you have some?
Yes, yeah, you come up. Or actually, there's no mic here, so just if you just speak loud, that's fine.
Yeah.
Okay, so that's a good question. So I don't have a neural network, so it is just the traditional like adjacency matrix based network. So it's just a matrix, but it does capture both the fluid to structure as well as the structure to fluid interaction. So yeah, it is embedded in that adjacency matrix. The only caveat is that you need to build a time varying adjacency matrix through the data. So as the data comes, you basically build the adjacency matrix, but it's time varying. But we've actually, based on whatever we've done, we've actually seen there are paths